Chapter 21 of Astronomy, the Science of the Heavenly Bodies, by David Todd. The Story of Astronomical Photography. The most powerful ally of both telescope and spectroscope is photography. Without it, the marvelous researches carried on with both these types of instrument would have been essentially impossible. Even the great telescopes of Herschel and Lord Rosse, notwithstanding their splendid record as optical instruments, might have achieved vastly more had photography been developed in their time to the point where the astronomer could have employed its wonderful capabilities as he does today. And with the spectroscope, it is hardly too much to say that no investigator ever observes visually with that instrument anymore. Practically every spectrum is made a matter of photographic record first. The observing, or nowadays the measuring, is all done afterward. All telescopes and cameras are alike, in that each must form or have formed within it an image by means of a lens or mirror. In the telescope, the eye sees the fleeting image. In the camera, the process of registering the image on a plate or film is known as photography. Daguerre first invented the process, silver film on a copper plate, in 1839. The year following, it was first employed on the moon. In 1850, the first star was photographed. In 1851, the first total eclipse of the sun, all by the primitive daguerreotype process, which, notwithstanding its awkwardness and the great length of exposure required, was found to possess many advantages for astronomical work. About the middle of the last century, the wet plate process, so called because the sensitized collodion film must be kept moist during exposure, came into general use, and the astronomers of that period were not slow to avail themselves of the advantages of a more sensitive process, which, in 1872, in the skilful hands of Henry Draper, produced the first spectrum of a star. In 1880 a nebula was first photographed, and in 1881 a comet. Before this time, however, a new dry plate process had been developed to the point where astronomers began to avail of its greater convenience and increased sensitiveness, even in spite of the coarseness of grain of the film. 40 years of dry plate service have brought a wealth of advantages scarcely dreamed of in the beginning, and nearly every department of astronomical research has been enhanced thereby, while many entirely new photographic methods of investigation have been worked out. Continued improvement in photographic processes has provided the possibility of pictures of fainter and fainter celestial objects, and all the larger telescopes have photographed stars and nebulae of such exceeding faintness that the human eye, even if applied to the same instrument, would never be able to see them. This is because the eye, in 10 or 12 seconds of keen watching, becomes fatigued and must be rested, whereas the action of a very faint light rays is cumulative on the highly sensitive film, so that a continuous exposure of many hours' duration becomes readily visible to the eye on development. So a supersensitive dry plate will often record many thousand stars in a region where the naked eye can see but one. Perhaps the greatest amplification of photography has taken place at the Harvard University under Pickering, where a library of many 100,000 plates has accumulated, and at Groningen, Holland, where Kapteyn has established an astronomical laboratory without instruments except such as are necessary to measure photographic plates, whenever and wherever taken. So it is possible to select the clearest of skies all over the world for exposure of the plates and bring back the photographs for expert discussion. Of course, the sun was the celestial body first photographed, and its surpassing brilliance necessitates reduction of exposure to a minimum. In moments of exceptional steadiness of the atmosphere, a very high degree of magnification of the solar surface on the photographic plate is permitted, and the details information, development and ending of sunspots are faithfully registered. Nevertheless, it cannot be said that photography has yet entirely replaced the eye in this work, and careful drawings of sunspots at critical stages of their life are capable of registering fine detail which the plate has so far been unable to record. Janssen of Paris took photographs of the solar photosphere so highly magnified that the granulation of willow leaf structure of the surface was clearly visible, and its variations traceable from hour to hour. The advantages of sunspot photography are ascertaining the sun's rotation, keeping count of the spots, and in a permanent record for measurement of position of the sun's axis and the spot zones are obvious. In direct portrayal of the sun's corona during total eclipses, photography has offered superior advantages over visual sketching, in the form and exact location of the coronal streamers, but the extraordinary differences of intensity between the inner corona and its outlying extensions are such that halation renders a complete picture on a single plate practically impossible. The filamentous detail of the inner corona and the faintest outlying extension of streamers the eye must still reveal directly. In solar spectrum photography, research has been especially benefited. Indeed, exact registry of the multitudinous lines was quite impossible without it. Photographic maps of the spectrum by Thollon, MacLean and Rowland are so complete and accurate that no visual charts can approach them. Rowland's great photographic map of the solar spectrum spread out into a band about 40 feet in length, and in the infrared, Langley's spectrobolometer extended the invisible heat spectrum photographically to many times that length. At the other end of the spectrum, special photographic processes have extended the ultraviolet spectrum far beyond the ocular limit, to a point where it is abruptly cut off by absorption of the Earth's atmosphere. On the same plate, with certain regions of the sun's spectrum, the spectra of terrestrial metals are photographed side by side, and exact coincidences of lines show that about 40 elemental substances known to terrestrial chemistry are vaporized in the sun. Young was the first to photograph a solar prominence in 1870, and 20 years later Deslandres of Paris and Hale of Chicago independently invented the spectroheliograph, by which the chromosphere and prominences of the sun, as well as the disk of the sun itself, are all photographed by monochromatic light on a single plate. Hale has developed this instrument almost to the limit, first at the Yerkes Observatory of the University of Chicago, and more recently at the Mount Wilson Observatory of the Carnegie Institution, where spectroheliograms of marvelous perfection are daily taken. It was with this instrument that Hale discovered the effect of an electromagnetic field in sunspots which has revolutionized solar theories, a research impossible to conceive of without the aid of photography. When we apply Doppler's principle, photography becomes doubly advantageous. Whether we determine, as Düner did, and more recently Adams, the sun's own rotation, and find it to vary in different solar latitudes, the equator going fastest, or apply the method to the sun's corona at the east and west limbs of the sun, which Deslandres in 1893 proved to be rotating bodily with the sun, because of the measured displacement of spectral lines of the corona in juxtaposition on the photographic plate. In the solar astronomy of measurement, too, photography has been helpfully utilized, as in registering the transits of Mercury over the sun's disk, for correcting the tables of the planet's orbital motion, and most prominently in the action taken by the principal governments of the world in sending out expeditions to observe the transits of Venus in 1874 and 1882, for the purpose of determining the parallax of Venus and so the distance of the Earth from the Sun. In our studies of the Moon, photography has almost completely superseded ocular work during the past 60 years. Rutherford and Draper of New York, about 1865, obtained very excellent lunar photographs with wet plates, which were unexcelled for nearly half a century. The Harvard, Lick and Paris observatories have published pretty complete photographic atlases of the Moon, and the best negatives of these series show nearly everything that the eye can discern, except under unusual circumstances. Later lunar photography was taken up at the Yerkes Observatory, and exceptionally fine photographs on a large scale were obtained with the 40-inch refractor, using a color screen. More recently, the 60-inch and 100-inch mirrors of the Mount Wilson Observatory have taken a series of photographs of the Moon far surpassing everything previously done, as was to be expected from the unique combination of a tranquil mountain atmosphere with the extraordinary optical power of the instruments, and a special adaptation of photographic methods. During lunar eclipses, Pickering has made a photographic search for a possible satellite of the Moon, occultations of stars by the Moon have been recorded by photography, and Russell of Princeton has shown how the position of the Moon among the stars can be determined by the aid of photography with a high order of precision. The story of planetary photography is on the whole disappointing. Much has been done, but there is much that is within reach, or ought to be, that remains undone. From Mercury nothing ought perhaps to be expected. On many of the photographs of the transit of Venus, especially those taken under the writer's direction at the Lick Observatory in 1882, we have unmistakable evidence of the planet's atmosphere. Here again the wet plate process, although more clumsy, demonstrated its superiority over the dry process used by other expeditions. In spectroscopy, Belopolsky has sought to determine the period of rotation of Venus on her axis. At the Lowell Observatory, Douglas succeeded in photographing the faint zodiacal light, and very successful photographs of Mars were taken at this institution as early as 1905 by Slipher. 2 years later these were much improved upon by the writer's expedition to the Andes of Chile, when 12,000 exposures of Mars were made, many of them showing the principal canali and other prominent features of the planet's disk. At subsequent opposition of the planet, Barnard at the Yerkes Observatory and the Mount Wilson observers have far surpassed all these photographs. For future oppositions a more sensitive film is highly desired, in connection with instruments possessing greater light-gathering power, so permitting a briefer exposure that will be less influenced by irregularities and defects of the atmosphere. The spectrum of Mars is of course that of sunlight, very much reduced, and modified to a slight extent by its passing twice through the atmosphere of Mars. What amount of aqueous vapour that atmosphere may contain is a question that can be answered only by critical comparison of the Martian spectrum with the spectrum of the Moon, and photography affords the only method by which this can be done. Many are the ways in which photography has aided research on the asteroid group. Since 1891 more than 600 of them have been discovered by photography, and it is many times easier to find the new object on the photographic plate than to detect it in the sky, as was formerly done by means of star charts. The planet, by its motion during the exposure of the plate, produces a trail, whereas the surrounding stars are all round dots or images. Or by moving the plate slightly during exposure, as in Metcalfe's ingenious method, we may catch the planet at that point where it will give a nearly circular image, and thus be quite as easy to detect, because all the stars on the same plate will then be trails. Photographic photometry of the asteroids has revealed marked variations in their light, due perhaps to irregularities of figure. On account of their faint light, the asteroids are especially suited, as Mars is not, to exact photography for ascertaining their parallax, and from this the Sun's distance when the asteroid's distance has been found. Many asteroids have been utilized in this way, in particular Eros 433. In 1931 it approaches the Earth within 13 million miles, when the photographic method will doubtless give the Sun's distance with the utmost accuracy. Photographs of Jupiter have been very successfully taken at the Yerkes and Lowell observatories and elsewhere, but the great depth of the planet's atmosphere is highly absorptive, so that the impression is very weak in the neighbourhood of the limb, if the exposure is correctly timed for the centre of the disc. The striking detail of the belts, however, is excellently shown. Wood of Baltimore has obtained excellent results by monochromatic photography of Jupiter and Saturn with the 60-inch reflector on Mount Wilson. Jupiter's satellites have not been neglected photographically, and Pickering has observed hundreds of the eclipses of the satellites by a sort of cinematographic method of repeated exposures, around the time of disappearance and reappearance by eclipse. The newest outer satellites of Jupiter were all discovered by photography, and it is extremely doubtful if they would have been found otherwise. Saturn has long been a favourite object with the astronomical photographer, and there are many fine pictures, in spite of its yellowish light, relatively weak photographically. The marvellous ring system with the Cassini division, the oblateness of the ball, the occasional markings on it, all are well shown in the best photographs, but the call is for more light and a more sensitive photographic process. Pickering's ninth satellite, Phoebe, was discovered by photography, one of the faintest moons in the solar system. Like the faint outer moons of Jupiter, few existing telescopes are powerful enough to show it. Its orbit has been found from photographic observations, and its position is checked up from time to time by photography. But the crowning achievement of spectrum photography in the Saturnian system is Keeler's application of Doppler's principle in determining the rate of orbital motion of particles in different zones of the rings, thereby establishing the Maxwellian theory of the constitution of the rings beyond the possibility of doubt. For Uranus and Neptune, photography has availed but little, except to negative the existence of additional satellites of these planets, which doubtless would have been discovered by the thorough photographic search which has been made for them by the W.H. Pickering without results. As with the asteroids, so with comets. Several of these bodies have been discovered by photography, none more spectacular than the Egyptian comet of May 17, 1882, which impressed itself on the plates of the corona of that date. Withdrawal of the sun's light by total eclipse made the comet visible, and it had never been seen before, nor is it known whether it will ever return. In cometary photography, much the same difficulties are present as in photographing the corona. If the plate is exposed long enough to get the faint extensions of the tail, the fine filaments of the coma or head are obliterated by halation and overexposure. No one has had greater success in this work than Barnard, whose photographs of comets, particularly at the Lick Observatory, are numerous and unexcelled. His photographs of the Brooks comet of 1893 revealed rapid and violent changes in the tail, as if shattered by encounter with meteors, and the tail of Halley's comet in 1910 showed the rapid propagation of luminous waves down the tail, similar to phenomena sometimes seen in streamers of the aurora. Draper obtained the first photograph of a comet's spectrum in 1881, disclosing an identity with hydrocarbons burning in a Bunsen flame, also Bunsen the violet due to carbon compounds. The photographic spectra of subsequent comets have shown bright lights due to sodium and the vapour of iron and magnesium. Even the elusive meteor has been caught by photography, first by Wolf in 1891, who was exposing a plate on stars in the Milky Way. On developing it, he found a fine, dark, nearly uniform line crossing it due to the accidental flight across the field of a meteor of varying brightness. Since then, meteor trails have been repeatedly photographed, and even the trail spectra of meteors have been registered on the Harvard plates. At Yale, in 1894, Elkin employed a unique apparatus for securing photographic trails of meteors. 6 photographic cameras mounted at different angles on a long polar axis driven by clockwork, the whole arranged so as to cover a large area of the sky where meteors were expected. When we pass from the solar system to the stellar universe, the advantages of photography and the amplification of research due to its employment as accessory in nearly every line of investigation are enormous. So extensively has photography been introduced that plates, and to a slight extent films, are now almost exclusively used in securing original records. Regrettably so in case of the nebulae, because the numerous photographs of the brighter nebulae taken since 1880, when Draper got the first photograph of the nebulae of Orion, are as a rule not comparable with each other. Differences of instruments, of plates, of exposure and development all have occasioned differences in portrayal of a nebula which do not exist. When we consider faithful accuracy of portrayal of the nebulae for purposes of critical comparison from age to age, many of our nebular photographs of the past 40 years, fine as they are and marvellous as they are, must fail to serve the purpose of revealing progressive changes in nebular features in the future. Roberts and Common in England were among the first to obtain nebular photographs with extraordinary details, also the brothers Henri of Paris. As early as 1888, Roberts revealed the true nature of the great nebula in Andromeda, which had never been suspected of being spiral, and Keeler and Perrin at the Lick Observatory pushed the photographic discovery of spiral nebulae so far that their estimates fill the sky with many hundred thousands of these objects. In the southern hemisphere, the 24-inch Bruce telescope of Harvard College Observatory has obtained many very remarkable photographs of nebulae, particularly in the vicinity of Eta Carinae, but the great reflectors of the Mount Wilson Observatory, on account of their exceptional location and extraordinary power, have surpassed all others in the photographic portrayal of these objects, especially of the spiral nebulae, which appear to show all stages in transition from nebula to star. No less remarkable are the photographs of such wonderful clusters as Omega Centauri, a perfect visual representation of which is wholly impossible. Intercomparison of the photographs of clusters has afforded Bailey of Harvard, Shapley of Mount Wilson, and others the opportunity of discovery that hundreds of the components of stars are variable. What is the longest photographic exposure ever made? At the Cape of Good Hope, under the direction of the late Sir David Gill, exposures of nebulae were made, utilizing the best part of several nights, and totaling as high as 17 or even 23 hours. But the Mount Wilson observers have far surpassed this duration. To study the rotation and radial velocity of the central part of the nebula of Andromeda, an exposure of no less than 79 hours total duration was made on the exceedingly faint spectrum, and even that record has since been exceeded. The eye cannot be removed from the guiding star for a moment while the exposure is in progress, and this tedious piece of work was rewarded by determining the velocity of the centre of the nucleus as a motion of approach at the rate of 316 km per second. But when the stars, their magnitudes and their special peculiarities are to be investigated en masse, photography provides the facile means for researches that would scarcely have been dreamed of without it. The International Photographic Chart of the entire heavens, in progress at 20 observatories since 1887, the photographic charts of the northern heavens at Harvard and of the southern sky at Cape Town, the manifold investigations that have led up to the Harvard photometry, and the unparalleled photographic researches of the Henry Draper Memorial, enabling the spectra of many 100,000 stars to be examined and classified. All this is but a part of the astronomical work in stellar fields that photography has rendered possible. Then there are the stellar parallaxes, now observed for many stars at once photographically, when formerly only one star's parallax could be measured at a time and with the eye at the telescope, and photoelectric photometry, measuring smaller differences of light than any other method, and providing more accurate light curves of the variable stars. And perhaps most remarkable of all, the radial velocity work on both stars and nebulae, giving us the distance of the whole classes of stars, discovering large numbers of spectroscopic binaries, and checking up the motion of the solar systems toward Lyra within a fraction of a mile per second. All told, photography has been the most potent adjunct in astronomical research, and it is impossible to predict the future with more powerful apparatus and photographic processes of higher sensitiveness. The field of research is almost boundless, and the possibilities practically without limit. What would Herschel have done with £100,000 and photography? End of chapter 21.